We now want to look at conservative forces in a little more detail. So the definition of a conservative force is a force where if I calculate the work done over a closed path, then the total work done is zero. All right, so that's what the integral with the circle through it means. It's a closed path. So I'm looking at where an object starts, and then some work is done to it, and it moves, and then it comes back to its original position, and I want to calculate the total amount of work done on that object by a given force. All right, so let's look back at the brick. And if I have a brick resting on a surface, and it's lifted up from point A on the ground, upward by a crane to point B, then the definition of the work integral, okay, is going to be from point A to point B, the integral of point A to point B of f dot dr. And here we're looking at the force of gravity, and we're trying to show that gravity is conservative, okay? So this is the force of gravity, and dotted into the path that the object is taking from position A to position B. So as the object is rising, okay, gravity is always acting downward, so F is always going to be negative mg. Okay, so this is the integral from A to B of negative mg dot dr. And since the force and the displacement are in the same direction, actually they're anti-parallel in this case, then the cosine of the angle between them goes to 1, and we can just write it as this. And mg is constant, so this can come out of the integral. And this is just the integral of dr from A to B. But the integral of dr is just r, and from A to B, this becomes b minus a. So we can see that as I lift an object, if I let my origin be the ground here, then as I lift my object up to a certain height b, then the work is going to be negative. The work that gravity is doing, not the work the crane is doing, but the work that gravity is doing on the object is going to be negative. Okay, that is an explicit important point, explicitly important point. We're talking about the work that gravity is doing, not the work that the crane has done, but the work that gravity has done as the object is lifted. And gravity is always a downward force, and if we have a positive coordinate system upward, then we're always going to have this minus sign. And because if our ground is our origin, then B is always going to be greater than A, so this is always going to be a positive value. And in fact, if the ground is our origin, then A is typically going to be set to 0, and B is just simply the height that the object has been raised to. Now, as I said, a conservative force has a value of 0 for the integral over a closed path. So now, after the brick has been raised up to a height b, we let it drop and fall back down to its original position. And so now we have to calculate the amount of work that was done by gravity in dropping the object. And the whole idea is that this integral, broken up into these two pieces, the piece where the crane is lifting it up and the piece where the crane is dropping it, are going to cancel each other out, and the total work will be 0. And if we can do that, then we can show that gravity is indeed conservative. Okay? And so F dot dr, now gravity is acting downward and the displacement is downward, so they're in the same direction. And so the cosine of the angle between them is again 1. And I can write negative mg dr from this time b to a. And so this is going to be negative mg. And again, if a is 0, right? If a is 0, then this is just 0 minus b. And so now my negative signs cancel out, and I have mgb. And as you can see, the work done, and again, B is just the height of the object being dropped from in this case. So the amount of work done by gravity as the object is being lifted is negative mgh, and the work done by gravity as the object is falling is mgh. And this is, I guess, is explicitly stating that the difference between these is h. And this is indeed 0. And so because the total amount of work done by gravity on my object as I lift it and then it falls back down is 0, therefore gravity is a conservative force. And that's one way to interpret this integral. Now this is a nice example because the forces are constant. It takes a little bit more math when the forces are not constant, but the idea of the closed integral is the same. You're just looking at a closed path, starting point, and then it comes back to that starting point. If the total amount of work done over that path is 0, then the force will be conservative. All right, we'll see you next time.